you have heard now that stress is a tensor. I would like to now tell you what is a tensor. You have come across quantities like scalar. You remember the examples are mass, density, temperature, they have simply magnitude. You have also come across vector. Examples are forces, moments, in this case you have magnitude and also a direction. So, they have one more attribute. In fact, all quantities that engineer and physicists come across, they are nothing but tensor. Scalar, vector, they are also tensor. So, tensor is a more general quantity. Example of tensor can be of different order. Let us look into how we define the order or the rank of a tensor. In fact, this order or rank is defined by the number of attributes. We have 0 rank tensor, and they are nothing but scalar, and examples I have already given: mass, density, temperature, and we can represent them by symbols like mass, let us say m, density by rho, and temperature by T. Then we have first rank tensor. They are nothing but vector. We can represent them by symbols like Fi, Mi. Fi, in the case of 3 dimensions, I can have 3 components, one in the x, then in the y and z direction. So, therefore, there are 3 components. So, they have magnitude plus the directions, and there is one index to indicate the first rank tensor. Similarly, we have second rank tensor. Stress, examples are stress, strain, in the case of stress, you have seen that we have magnitude of stress, it has a direction of action, and at the same time it has also a plane of association. So, therefore, there is one more attribute, and we generally represent the stress by symbols sigma ij. So, there are 2 attributes, therefore, there are 2 indices. Similarly, in the case of strain, we represent by symbol epsilon, and there are also 2 indices used to indicate the rank of the tensor. In fact, in stress analysis and strength of materials, we will have one more tensor, which is 4th rank tensor, and this is material property tensor. Material property. In fact, the stresses and strains are related and they are related by a relationship of the type which we can write sigma I j is equal to some property tensors f e I j k l epsilon k l. So, there are 4 indices and it is a 4th rank tensor. So, we should be now on be careful in trying to differentiate between stress and a vector. Now, we would like to consider how we can quantify the deformation at a point or define the strains at a point. In order to define the strain at a point, I would like to go in for considering a 2-dimensional case for convenience, but it can be easily extended to 3 dimensions. So, let us consider a thin disc subjected to forces which are like this, and the body is in equilibrium and it is just deforming. Under the action of these forces, each of the point in the body is going to have some movement in the x direction. Let us represent by the let us represent this movement by symbol u, and it is also going to have some displacement under the action of the loading in the y direction, which is equal to v. This value of the displacement is going to vary from point to point, and therefore, this u displacement is certainly a function of position of the point. So, u x y function of x y. So, also v displacement is a function of the position x y. And in case of 3 dimensions, so this is the picture in 2 dimension. If we consider 3 dimensions, then we are going to have the displacements like u, v, and one displacement in the z direction, which we generally indicate by w. So, therefore, in the case of 3 dimensions, we are going to have displacements u, which is a function of x, y, z. So, also v, which is going to be function of x, y, z, and then we will have displacement w, which is also function of x, y, z. Now, we will try to see the deformation at a point, let us say point A, or rather we would like to calculate the strains or quantify the strains at the point A after the body has undergone deformation. In order to do that, we consider a very small element like this, and if we draw to a larger scale, let us draw to a larger scale this particular element. So, this is the element A, let us say this is A, B, and then C and D. Now, after deformation, this particular element is going to change position and it is going to have a shape. Let us say that displaced position of this element will indicate by this. So, this is the deformed position of the element. Therefore, A has shifted to A dash, B to B dash, and this is shifted to C dash, and this is shifted to D dash. Let us consider that the distance between AB is delta x, which is small, distance between AD is delta y. Now, point A has shifted by a distance u in the x direction and it has shifted by some distance v in the y direction. So, therefore, this is nothing but u and this distance is nothing but v. So, these are the displacement of the point A. Since it is a continuous body, you will find that this function u and v, they are continuous functions. There is no jump in the function as you move from point to point over this area of the body. Now, if I want to calculate the displacement at the point B, I can calculate it from the displacement of the point A, from the consideration that the two are at a distance delta x, which is very small, and we can consider expanding this u in Taylor series, and then we can write the displacement of the point B in the x direction. Let us say that is the displacement of the point in the x direction B to B1. So, this B to B1, we can write this thing as BB1 is equal to u of the point A plus rate of change of u with respect to x multiplied by delta x. So, that is the displacement BB1. Similarly, if we calculate this distance B1 B dash, it can be obtained from the displacement v of the point A. So, this should be nothing but v plus rate of change of v with respect to x multiplied by delta x. So, that is again by Taylor series expansion. Similarly, if we consider the point D, it has shifted to D1 in the y direction and then it has shifted to D dash in the x direction. So, therefore, by similar consideration, we can write that DD1 is nothing but v delta y del y, and this distance d1 d dash is equal to, it is again obtainable from u delta y del y. So, therefore, these are the displacements. Now, we would like to calculate the strains at the point A, and the strains are defined like this. Strains at the point A in the x direction, which is represented by epsilon xx, or in short epsilon x, it is nothing but rate of change of deformation of AB in the x direction. So, therefore, it is given by and also that rate of change of deformation as delta x tends to 0, that gives us the strain at A. So, therefore, it is defined by delta x tending to 0, it is the deformed length is A dash B dash, original length is AB divided by the original length. So, therefore, that is the rate of change of length, and as delta x tends to 0, that gives us the strain at A in the x direction. In fact, this A dash B dash, since this angle here, this angle is, let us say this angle is gamma 1, is very small, we can approximate this distance A dash B dash by this distance A dash B2. So, therefore, we can write that this limit is given by, it is A dash B2 minus AB by AB. Now we can write this thing very easily to be given by limit delta x tending to 0, and this A dash B2 is nothing but delta x plus BB1. So delta x plus BB1 minus the distance u, so minus u, that's what is this, minus AB, which is nothing but delta x, and this is delta x. Now BB1 is nothing but u plus delta u delta x del x. So therefore we will cancel u, and then we will be also having cancellation of this delta x, and this finally will give us limit delta x tending to 0 delta u delta x by delta x, and therefore this is delta u delta x. So the strain in the x direction epsilon x is nothing but partial derivative of u with respect to x. So that is the strain in the x direction. Now let us calculate the strain in the y direction. So we will again confine ourselves to the deformation here, and the strain in the y direction is defined as the deformation of AD in the y direction as this length delta y tend to 0, that is the strain in the y direction at point A, and it is given by epsilon yy, or in short epsilon y, and that is equal to limit delta y tending to 0, this is A dash d dash minus AD divided by AD. Now we can write this thing again as, we can approximate A dash d dash again by a consideration like this. We can draw this parallel to y axis, and if we consider this point to be D2, since this angle, let us say this gamma 2 is very small, we can now approximate A dash d dash by A dash D2. So it is A dash D2 minus AD by AD, and since DD1 is known and this displacement V is known, DD1 is nothing but V plus delta V delta y, then we can write this thing as, suppose this is, I think we should write this thing approximate, not exactly equal to, and therefore if we now substitute the value, we get limit delta y tending to 0, and this is delta y plus A dash this is D, I am sorry, this should be D D1 minus V minus the original length is delta y divided by delta y, and this DD1 is equal to V plus delta V delta y. So this V and this V will cancel, this delta y will cancel, so therefore DD1 only this part will be remaining, and on simplification what we get is that del epsilon y is equal to limit delta y tending to 0, it is delta V delta y del y by del y, and therefore this is equal to delta V delta y. So, the strain in the y direction is nothing but partial derivative of v in the y direction, or slope of the v surface in the y direction. Similarly, your strain in the x direction, it is nothing but slope of the u surface in the x direction. Now, we would like to consider the shear strain. Shear strain is defined as the change in the angle between two orthogonal directions under the action of external loading. Herein, we had AB and AD, two orthogonal directions, and after deformation they have become A dash B dash and A dash D dash, and therefore there has been a change in the angle with original 90° by the amount gamma 1 and gamma 2, and this shear strain in 2 dimension gamma xy is defined by limit delta x tending to 0. So, as this length of the elements is shrunk to 0, the limit gamma 1 plus gamma 2, that gives us the value of the shear strain. Now, we can calculate the shear strain as follows. We can now write that this is approximately equal to limit delta x tending to 0, delta y tending to 0, that this angle I can approximate it by that this is b2 b dash divided by distance a2 b2. So, this is nothing but b2 b dash divided by a dash b2, that is gamma 1, plus we have here this gamma 2 is nothing but d2 d dash divided by the length a dash d2. So, this is what is the shear strain. Now, if we see that b2 b dash, this whole distance b2 b dash is nothing but, it is going to be v plus, it is nothing but, we have this distance is given by b1 b dash minus b1 b2, which is nothing but v. So, therefore, this distance is nothing but delta v delta x del x. So, therefore, this distance is nothing but delta v delta x del x. So, therefore, this is this distance, and similarly here this distance, we can write this distance, it is nothing but this total distance, which is d1 d dash minus this distance u. So, therefore, it is delta u delta y del y. So, therefore, this is delta u delta y, I am sorry, this distance is nothing but delta u delta y del y. So, if we consider that this distance is nothing but this total distance minus this one, and which is therefore is given by delta u delta y del y. So, therefore, if we substitute all this, what we find now, what we get now is this, that limit delta x tending to 0, delta y tending to 0, this is delta v delta x del x divided by this distance a dash b2 is nothing but delta x plus delta u delta x del x plus this d2 d dash is nothing but delta u delta y del y divided by delta y plus delta v delta y plus del y. So, this distance we can also consider to be this distance as original length plus rate of change of v with respect to y multiplied by delta y. Similarly, this distance to be equal to original length plus rate of change of u with respect to x. So, that gives us the length of the sides a dash b2 and a dash d2. So, now if you simplify all this, it gives us now delta v delta x by 1 plus delta u delta x, and this is delta u delta y 1 plus delta v delta y. In fact, the strains are very small compared to unity. So, therefore, we can neglect these quantities, and therefore, we can write this thing for small deformation. This is nothing but delta v delta x plus delta u delta y. So, these quantities can be neglected, and we get the strains finally to be given by gamma xy is equal to delta u delta y plus delta v delta x. So, it is the sum of the cross derivatives that gives you the shear strain at the point A that we have been considering. Now, this shear strain is known as engineering shear strain. We define the tensorial shear strain like this, that epsilon xy is equal to half of engineering shear strain, and therefore, this is equal to half delta u delta y plus delta v delta x. So, this is tensorial shear strain. I want you to note one point carefully, that when we are trying to consider the element which we had started with, you see here this side rotates by gamma 1, and this side is rotating in the opposite direction, anticlockwise direction, and this is rotating in the clockwise direction, this is rotating in the anticlockwise direction, and this gamma 1 is, and this is gamma 2, we generally take it to be gamma 1 equal to gamma 2, and that is equal to half of gamma xy, and this gamma 1 is the rotation of the x direction in the x axis in the y direction. So, this gamma 1 is nothing but rotation of the x axis in the y direction. Similarly, this gamma 2 can be considered to be rotation of the y axis in the x direction, and therefore, we represent them by symbols. Gamma 1 is nothing but epsilon xy, rotation of x axis in the y direction, and gamma 2 to be rotation of y axis in the x direction. So, these are the tensorial shear strain, and in fact, since gamma 1 equal to gamma 2, we have shear strains epsilon xy is equal to epsilon yx. Finally, therefore, at a point we have the strains like epsilon x, epsilon xy, and epsilon yx, epsilon y. So, these are the strain associated with the x directions, these are the strains associated with the y direction. This is known as 2D strain tensor. And in the initial notation, we can write this thing as epsilon 11, epsilon 12, epsilon 21, epsilon 22. And in short, we indicate this thing as epsilon ij with the implicit assumption that I takes up value 1 to 2 and j takes up value 1 to 2. So, therefore, this is the two dimensional strain tensor epsilon ij. We can extend this consideration to 3 dimensions, and in 3 dimensions we will have the strains like epsilon x axis rotating in the y direction, epsilon xz x axis rotating in the z direction. Similarly, we will have epsilon y axis rotating in the x direction, direct strain, and then we have epsilon y axis rotating in the z direction. Similarly, epsilon zx, epsilon zy, and epsilon z. So, these are the 9 components of strain tensor in 3 dimensions. And in initial notation, we can again write, and then we can also write in short epsilon ij with the implicit assumption that I takes up value 1 to 3, j takes up value 1 to 3. So, therefore, it is a 2 dimensional, I am sorry, this is a 3 dimensional stress tensor. And you also note that we have the condition that epsilon xy is equal to epsilon yx, similarly epsilon xz is equal to epsilon zx, and then epsilon yz is equal to epsilon zy. So, therefore, these shear strengths components are equal, and therefore, we have this equal to this component is equal to this component, and again this component is equal to this component. So, therefore, the strain tensor is also a symmetric tensor. So, it is also symmetric. It is also a symmetric tensor. Now, we have got engineering strain tensor, which is like this. In the case of 3 dimension, it will be epsilon x, and it will be gamma xy, gamma xz, and this is gamma yx, epsilon y, gamma yz, gamma zx, gamma zy, epsilon z. So, this is engineering strain tensor. Herein the difference is that the shear strains are double of the tensor shear strain, and this is also symmetric. The tensorial definition is very important, because both stress and strain, we have symbol for stress is sigma ij, symbol for strain is epsilon ij. Now, this is going to be helpful. Engineering, this tensor definition of shear strain will be helpful, because whatever relations we write for sigma ij can be directly adopted for epsilon ij. So, this tensor definition is that way very useful. Now, convention for positive strain and negative strain I would like to give. Sign convention. If we have, let us say that the strains let us say that this strain at a point is given by value like 10 to 10 to the minus meter per meter, and this is let us say 10 to the power minus 6, and this is 10 to the power minus 6, and this is let us say 5 into 10 to the power minus 6, and these are strain. So, it should be unit like meter per meter. So, they are dimensionless. So, meter per meter. Now, what it means that this strain is positive, epsilon x is equal to 10, we sometimes write it as micro strain. So, this strain micro strain, it is positive. So, therefore, it is causing elongation. So, also epsilon y is equal to 5 micro strain, it is causing elongation in the y direction, whereas this strain is causing epsilon xy is equal to minus 10 micro strain, it is causing a change in the angle. So, this must be understood that if you have an element like this, this particular deformation is such that this angle in the first quadrant is going to increase. So, this is really the angle has now increased. So, therefore, this means that the angle is increasing, that deformation is different. If it is positive, let us say epsilon xy is equal to let us say 15 micro strain, then the deformation would be like this. The deformation will give rise to the angle of this sort in the first quadrant. So, therefore, this is going to be the final angle. So, please note that this epsilon xy, when it is negative, it is going to be increase in the angle over 90 degree, and this is positive, means it is going to indicate a decrease. So, these are the conventions which are followed for strains. You must be wondering why this epsilon xy and epsilon yx, they are same. There is some physical reasoning behind that. Look at these stresses. So, if we consider the element to be subjected to stresses sigma x, sigma y, and the shear stresses. So, this is tau xy, this is tau yx, this is sigma x, this is tau xy, tau yx, then of course, we have also the sigma y stress here. This tau xy, this pair is trying to rotate the element like this. So, it does, this pair causes the rotation of the element like this. So, in fact, that is responsible for this rotation, what we indicated as gamma 1, and these two components tau yx, they are responsible for the rotation of the element like this. So, in fact, these components are responsible for rotating the elements like this. So, it is responsible for the rotation of the y axis in the x direction. So, therefore, you see that this rotation is nothing but gamma 2. So, these are the stresses tau xy, and these are the stresses tau yx. The element is square in shape, and therefore, see the rotation due to these stresses will have some magnitude. It will depend on the moment that is produced by them. Similarly, the rotation gamma 2 is going to be caused by these stresses, and the moment produced by them. So, therefore, it will depend on the magnitude. Since the dimension is the same, it is square. So, therefore, these two moments are going to depend on the magnitude of these two stresses, and you have seen that stress is a symmetric tensor, that thereby indicating that tau xy is equal to tau yx. Therefore, the moment produced by these two pairs is same as the moment produced by these two pairs, and hence there is nothing to see that these two rotations are going to be different. They must be the same, and hence we have, since this stress tensor is symmetric, we are going to see that this gamma xy is equal to gamma yx. Rotation of the x axis in the y direction is equal to rotation of the y axis in the x direction. That is why the two angles or shear strains are considered to be the same. So, we have now been able to quantify the stresses and strains at a point. It is also important to note that the shear strength expressions are that gamma xy is equal to delta u delta x plus delta v delta y. So, herein these two directions, and the definition of shear strain involves the two displacement involved. These two displacements are in the two Cartesian directions that we have here. By similar argument, we can say that delta gamma yz shear strain is nothing but we will have displacement v and w, and there will be cross derivative. So, therefore, this is delta w delta y plus delta v delta z, and gamma xz is equal to delta w delta x plus delta u delta z. So, these are the shear strains in 3 dimensions. Now, we would like to consider, if the stresses are given at a point by sigma ij, we are interested in trying to see what is going to be the traction on any arbitrary plane. So, this is known as, this is given by Cauchy formula. Or traction on an arbitrary surface. Now, these traces we can show it to be like this. So, let us consider the Cartesian directions as it is, and then we try to consider an arbitrary surface let us consider an arbitrary surface like this. So, let us say that this is my origin O, this is, let us say that this plane is A, B, C, Now, the stresses at the point O is given by sigma ij. So, we can represent the stresses by showing the stress component on the faces OCA, OAB and OBC. So, these are going to be like this, that we will have the stress component here, it is sigma x, and then its negative face. So, if you consider that this is your x direction, this face is negative. Similarly, let us show our axis x, y, z. So, this is sigma x, and now the shear stress is going to be directed like this. This is tau x y, and this other component is going to be like this. This is tau xz. Similarly, we will have the components like this. This is sigma y, and the other components are shear stress components are like this. This side we are going to have the normal components like this, sigma z, and the shear stress components are going to be this and this. Now, we are interested in finding out the traction on this area ABC arising out of the stresses at the point O. So, this is the area. Let us say area ABC is equal to A, and let us also consider that the outer normal to the plane ABC is directed like this. This is the outer normal. This outer normal would have some direction cosines. Its inclination with the x, y, z axis will cosine of the angle will indicate by the direction cosines L, M and N. These are the direction cosines. Then in that case, it is clear that area OAC is nothing but L into A, area OAB is nothing but M into A. Similarly, area OBC is equal to N into A. So, these are straight from the geometry. Now, we are interested in considering the traction on this face ABC. So, if we consider that the traction force per unit area on this plane ABC in the x direction, it will have three components. Of course, we will have three components. One in the x direction, we will represent that by Sx. Similarly, the component in the y direction will represent by Sy, and the component in the z direction this is Sz. So, this is Sz, this is Sy. So, these are the three components. Now, if we try to consider the equilibrium in the x direction, Fx equal to 0, the force in the x direction on this area is A into Sx acting in the positive x direction, and now we are going to have forces in the negative x direction arising out of sigma x acting on this area, which is nothing but L into A into sigma x. Then we will have forces coming from this stress, which is nothing but tau zx, and also this is tau yx. So, therefore, this force arising out of this component acting on an area is nothing but M into A multiplied by tau yx plus this component, which is acting on an area is equal to n into A into is tau Zx. So, therefore, this is what is the equilibrium equation in the x direction, and we can now write this simplified. It is Sx is equal to L into sigma x plus m into tau yx plus n into tau zx. I can write this equilibrium equation in the y direction. So, that will give me by similar consideration. It is very simple. You can find out the force in this y direction. It is force in this y direction is given by this traction, and it is balanced by the traction or forces coming up due to this stress. It is coming up due to the shear stress this one and the shear stress this one, and if you simplify it will look like this. It is going to be equal to L into tau xy plus m into sigma y plus n into tau zy. Similarly, if you consider the equilibrium in the z direction, it will give you Sz is equal to L tau, this is xz plus m into tau yz plus n into tau, I am sorry, this is sigma z. So, these are the three relations, this 1, 2 and 3, these are known as Cauchy formula. So, 1, 2 and 3 are Cauchy formula. So, to calculate the traction on any arbitrary plane, if you know the direction cosines of the plane and the stresses at the point, then you can calculate the tractions by this formula. And in indicial notations, if you make use of the indicial notations, we can write that S1 is equal to, it is L1 into sigma 11 plus L2 sigma 21 plus L3 into sigma 31. S2 is equal to L1 sigma 12 plus L2 sigma 22 plus L3 sigma 32, and S3 is equal to L1 sigma 13 plus L2 sigma 23 plus L3 sigma 33. In short, in tensor notation, these three relations can be written like this: Sj is equal to Li sigma j I. I am sorry, this is Sj equal to Lj sigma j I, wherein Sj is equal to, no, I am sorry, this is not correct. So, we have to write Sj is equal to Li sigma Ij. So, this is in indicial notation, and with the implication that I takes up value 1, 2, 3. So, also j takes up value 1, 2, 3. So, we get the traction, 3 tractions.